According to new research recently published in the journal Science, an ultrathin invention could make future computing, sensing, and encryption technologies remarkably smaller and more powerful by helping scientists control a strange but useful phenomenon of quantum mechanics. Scientists at Sandia National Laboratories and the Max Planck Institute for the Science of Light have reported on a device that could replace a room full of equipment to link photons in a bizarre quantum effect called entanglement. This device, a kind of nano-engineered material called a metasurface, paves the way for entangling photons in complex ways that have not been possible with compact technologies. When scientists say photons are entangled, they mean they are linked in such a way that actions on one affect the other, no matter where or how far apart the photons are in the universe. It is an effect of quantum mechanics, the laws of physics that govern particles and other very tiny things. Although the phenomenon might seem odd, scientists have harnessed it to process information in new ways. For example, entanglement helps protect delicate quantum information and correct errors in quantum computing, a field that could someday have sweeping impacts in national security, science and finance. Entanglement is also enabling new advanced encryption methods for secure communication. Research for the groundbreaking device, which is 100 times thinner than a sheet of paper, was performed in part at the Center for Integrated Nanotechnologies, a Department of Energy Office of Science user facility operated by Sandia and Los Alamos National Laboratories. The new metasurface acts as a doorway to this unusual quantum phenomenon. In some ways, it is like the mirror in Lewis Carroll's Through the Looking Glass, through which the young protagonist Alice experiences a strange new world. Instead of walking through their new device, scientists shine a laser through it. The beam of light passes through an ultrathin sample of glass covered in nanoscale structures made of a common semiconductor material called gallium arsenide. A pair of entangled photons at different wavelengths emerge from the sample in the same direction as the incoming laser beam. The researcher Brener is excited about this device because it is designed to produce complex webs of entangled photons, not just one pair at a time, but several pairs all entangled together and some that can be indistinguishable from each other. Some technologies need these complex varieties of so-called multi-entanglement for sophisticated information processing schemes. Other miniature technologies based on silicon photonics can also entangle photons, but without the much needed level of complex multi-entanglement. Until now, the only way to produce such results was with multiple tables full of lasers, specialized crystals, and other optical equipment. The science paper outlines how the teams successfully tuned their metasurface to produce entangled photons with varying wavelengths, a critical precursor to generating several pairs of intricately entangled photons simultaneously. However, the researchers note in their paper that the efficiency of their device, the rate at which they can generate groups of entangled photons, is lower than that of other techniques and needs to be improved. A metasurface is a synthetic material that interacts with light and other electromagnetic waves in ways conventional materials can't. Commercial industries are busy developing metasurfaces because they take up less space and can do more with light than a traditional lens. Now we can replace lenses and thick optical elements with metasurfaces. Those types of metasurfaces will revolutionize consumer products. Metasurfaces are leading to a paradigm shift in quantum optics, combining ultra-small sources of quantum light with far-reaching possibilities for quantum state engineering.